And got it. Come over here. Okay, welcome to, we don't have a whole lot of big data classes left. We have this class, and then next week we have two more. I guess we have our lab section tomorrow. Lab tomorrow, we're gonna be, you'll be playing around with the indexes and creating them and seeing the different algorithms. Postgres select the different algorithms in practice, so hopefully that'll make things a little bit more concrete. Today as well, we're going to be going over the this final practice problems 1 right here. And hopefully that will also start making things a little bit more concrete for you all about what you need to know for the final exam. Next week, we'll have a little bit more talking about indexes and indexes that are not B trees, but other types of indexes and why you might want to use those. And then that will be it for all of the graduating students. You'll have your final exams the following week. And the non-graduating students, still no like super new material, just that last sort of week of classes we'll be going over how to combine all this stuff together to create your own efficient web page that can serve queries instantaneously from gigabytes or terabytes of data. So again, if you have this final practice problems 1, start getting that ready. We'll be going over this in just a couple minutes here. Before we do that though, coming back over here, so on our class webpage, not on the topic 10, but in this issue over here. Ooh, and looks like I forgot an E right here in Postgres. But I've posted your last of the main homeworks for this class, this Twitter Postgres indexes. And again, this is like what all of the other homeworks, starting from the very beginning of the semester, but especially these most recent 2 Twitter Postgres homeworks have been building up to. Again, started at the beginning of the semester talking about how to make things, how to do queries without SQL, just in the shell, making them faster with things like MapReduce, then switching over to SQL, getting our SQL queries correct with Pagilla, then getting in data inserted fast with the last 2 Twitter Postgres assignments. And now we'll be doing SQL queries that are both correct and fast in this last assignment here. So everything's been building up just to this last assignment here. The most important thing that I want us to cover today, there's a lot of sort of background information related to this assignment. We're not going to be able to cover it all. You'll have to read through this on your own, but I'm going to highlight some of the important parts here. The first most important part of this assignment is related to the due date. So I've already extended the due date once for this assignment from next Tuesday to next Thursday, but we'll extend it even more for you all. I don't think the assignment is necessarily a particularly long assignment. Personally, when I was working through these, I think the parallel assignment was maybe the inserting thing in parallel, maybe the hardest one to do, just because there's this big set like Python code base that you have to sort of get familiar with. So I don't think it's necessarily like you need extra time for this assignment, but just because I know there's a lot of other things going on right now and give you all a little bit more flexibility with your schedules, I'm giving you extra time for that reason. So graduating students, you have until next Sunday, I guess that's 10 days from now, to submit the assignment without a late penalty. And if you, again, submit it later than that, I would just recommend that you do it before you have your final exam with me so that I can tell you exactly what your grade is, and then you have nothing else to do in the class. The non-graduating students, you'll have 1 extra week on top of that to complete the assignment. Some of especially the data loading code here can go, or sort of maxes out what the resources on the Lambda server. So really the only reason that I'm giving you all this extra week is just so that there's likely to be less conflicts with the graduating students. So the graduating student stuff will run, 10% faster or something. But so modified due dates. And again, these will be the last of these main programming assignments for the class. Any questions about anything administrative at this point? Yes, nothing. Question is, the homework that is due today, how is the grading going to work? Coming over here. So there are 6 of these test cases that that you will need to pass. There are 16 points total for this assignment. The sequential stuff is all stuff from the last of the assignments, and so I'm basically expecting all of these to be green, and I guess you would lose points if they're not green, but there's no points specifically assigned for these. Out of the parallel, the normalized, unbatched, and the denormalized are both the easiest things to do. So out of the 16 points here, you get 4 points for this one, 4 points for this one, and then 8 points for the batched. The batched one being the harder one and the most points. And those points, in order to get all of the points, you have to have all of the test cases passing. And down way at the bottom in the table down here, you have to have the appropriate runtimes. Does that answer your question? Cool. Good question. Any other questions about anything administrative? Okay. Yeah, I don't want to talk about any of the other homeworks anymore. We'll do a quick review of the stuff that we talked about last time related to B trees and indexes, and then we'll get into our new technical material here. So again, the main purpose of B trees, the reason why they're different than the balanced binary trees that you've seen in your previous classes, is because now instead of storing these trees inside of memory, we're storing them on the hard drive, and so having this large fan out allows us to reduce the number of disk seeks. Again, this little arm right here, every time this has to move, that's a very slow operation, taking like tens of milliseconds, which is an eternity, every time this arm has to move. So we don't want it to have to move. And the B tree is minimizing that movement. That's like the main purpose behind the B tree. We talked about the internal structure of the B tree a little bit. Then we talked about these table scanning strategies. We're going to review these again in detail in the context of our PDF assignment, PDF file over here, the final practice problems 1 here in a second. But again, there are 4 table scanning strategies, and the main thing to think about with table scanning strategies, what makes them a table scanning strategy is that they just solve select queries that look something simple like this, where you're selecting some columns from some table with some where condition. And there's nothing else going on inside of this select statement right here. The sequential scan is one that you can always use. And then there were the 3 different types of index scans, the index scan, the index-only scan, and the bitmap scan. And we'll review again the advantages and disadvantages of those as we talk about that PDF file. Other than the scanning strategies, the sorting strategies you have to know, there's 3 different types of sorts built into Postgres. The most common reason why you need to do a sort is because you have this order by clause up here. But you also might need to sort if the downstream strategy that you're using needs some sort of sorted data. So again, 3 sorting strategies here. The first one is the quick sort if there is no limit clause. So it's, again, the in log in runtime, you can't do better than that if you have to sort everything. But if you do have this limit clause, you can take advantage of that to get faster sorting with the top in heap sort. You get this faster runtime down here. And there's this workmem parameter as you're reading through the documentation. Again, there's those 6-ish links that you're required to read, and we're only in class covering maybe half the material from those links. You'll see this workmem parameter come up a lot, and it always is controlling like how much stuff is fitting in memory and how much stuff is going onto the hard drive. So this workmem parameter is going to control if you're doing these memory sorts or if you're doing an on the hard drive sort. That'll be something that you'll need to definitely know for the final exam. But again, sorting always super slow, so you want to avoid it if possible using an index. And coming back over here again to our picture of our index, recall that one of the properties of the B tree is that in these leaf nodes, everything is sorted according to whatever the values are that we've been inserting. And there's these little pointers between pages so that we can just do a single scan of the table without any seeks. All of these pages are located one right after the other on the hard drive. And so if we need sorted data and we have an index, then we can easily get that sorted data without doing any disk seeks and without doing any sorting computation. So it's another advantage of the B tree to make sure that you understand. Coming back over here. So that's the sorting overview. The aggregate strategies, there are two aggregate strategies in Postgres. And again, aggregates means somehow you're doing a group by clause in your query, or you have an aggregate function. Count, sum, max as examples. These two things, again, often combine together, but they don't have to be. The group aggregate and the hash aggregate, the main difference between these is that the group aggregate requires sorted input data, so that's its disadvantage, but everything else about the group aggregate is much better. So we would like to always do a group aggregate if possible. So if we have an index that's able to return things to us in sorted order without having to sort things manually, calling one of those expensive sort functions, then we get a group aggregate and get all these good advantages for us. But if we don't have that index that is giving us things in sorted order, then we'll probably have to use a hash aggregate it's still decent, but has these other disadvantages, and you'll need to know those for the final exam. We have not yet covered these join strategies down here. We'll get to that today. But before we get to that, we'll come over to this PDF file right here. We're on the final practice problems 1. We'll go through the first, half or so of this PDF file right now. Again, on the GitHub repository, there are 2 of these questions _ final review .pdf files, a number 1 and a number 2. We'll go over this number 1 in class. The number 2 is different. Up here at the top, you can see that the tables that I'm giving you, the schema of the database is a little bit different. It's still inspired by the tweets database that we're working with right now in your homework problems, but it just contains different tables from that database. The columns and the different properties of those columns slightly different, and so you'll have to think about those differently as you're working through these problems. So again, number 2 for you to work on your own, number 1 for us to do in class. And for your final exam, again, as you come into your final exam for you graduating students, I'll have just a sheet like this that'll have a very small number of tables, somehow inspired by the Twitter database. And you'll have that as your reference that you'll be answering questions based on. Those of you who are, again, non-graduating students, rather than having me provide the tables like this for you, you will be providing the tables based on the website that you create in the last couple weeks of the semester. Any questions about just the setup of where we're at right now before we actually get into the problems here? Okay, problem number 1. So recall that certain constraints create indexes on the appropriate columns and list the equivalent create index commands that are run by these constraints. So we haven't maybe explicitly talked about this, but every time you have a unique constraint in your database, there we go. Every time you have a unique constraint, UNIQUE, that implies that an index has been created. And if you think about it, like a unique constraint requires that you do some sort of search through the database in order to find if that previous value has been inserted. And so it makes sense that you would want to have an index on that column in order to do that search efficiently. So there's actually nothing in the SQL standard that requires that you have an index created for a unique constraint, but every database that's ever been created always implements these unique constraints by creating an index. And in this particular example down here, we have no place where we have the unique keyword used anywhere, but we do have places where we have these primary keys, primary key, primary key, primary key. And all of those primary keys, again, a primary key is equivalent to a unique and not null constraint, and so we have a unique index created for each of these primary keys. So down here, this would look something like create. So I'm going to do the very top one up here on this users table right here. Create index. And the actual command that is equivalent, that is being run inside of Postgres, also has this unique keyword right here, that if you run a create index command and you add this unique keyword after the word index, then it creates the unique constraint on the particular columns that you specify. So create index unique on users, and then in parentheses over here, ID users, id, and I just barely run out of space, id users, like that. And so this is an example of one of these indexes that has been created up here. And the fact that we have this unique keyword right here, this doesn't affect performance in any way. It doesn't affect how the index is stored. It doesn't affect what you can do with it. It doesn't affect any of the scanning strategies. It just makes it so that it adds the unique constraint on that particular column right there. For the tweets table, we have the similar constraint on id tweets. So let's go back to red here. Great. Index, and I will not write out the word unique to save space because it's not actually relevant to us on tweets, id tweets, like so. And one last primary key is maybe a slightly new syntax for us, that there are two different columns here that we are unique on both of those together. So you can have multiple ID tweets, that's okay. In this tweets mentions table, one tweet can mention multiple users. You can have multiple users in this table. One user can be mentioned by multiple tweets, but any given tweet can only mention any particular user once. So we're unique on the combination of id users and id tweets. And so down here, the last create index command would be on tweets underscore mentions, and then all the indexes that we've seen so far have had just one column inside of it, but this is going to have two columns inside of it, the id underscore tweets, comma, id underscore users. And we're going to see in a minute that it's going to be important that the order of these columns and how that will affect performance in different ways. But for now, the thing to understand is that up here, it's listed in this order. And so the index itself is also listed in that same order. Yes?
You said we wouldn't need to know about create index.
Question is the unique create index unique versus create index? Is that something that you need to know? The answer is yes, you do need to know that. The difference between a create index unique and just a regular create index, though, is that there is no change in any performance related characteristics. The only difference between adding the unique word right here and not adding the unique word is that it it enforces the unique constraint whenever you're doing the inserts or updates or deletes. So the reason I did not write out the word unique down here on these other two indexes is because for the purposes of this document right here, we're only thinking about performance runtime of select queries. And so the fact that the word unique is there or not is not relevant to us. And I was just saving space by not writing out the word unique there. Good question. Any other questions so far? Okay. So some databases might also create indexes on these foreign key constraints. It is often good practice to create indexes on your foreign key constraint. So here we have this in reply to user ID as an example, and there is no index on this, no index on this right here. No index. But one of the things that we saw, especially with the Pagilla assignment, where we're doing a whole bunch of joins together, is that these foreign keys are things that you often want to join on. And so later on in this document, and when we start talking about those join strategies as well, we'll see what are the performance implications of not having the index on this foreign key constraint right here. But at this point, the important thing is that by default, no index is created on these foreign key constraints. Similarly, if you have a null constraint, I don't have a null constraint here listed anywhere, or one of those check constraints, any other type of constraint that is not a unique constraint, it will not create an index. Only a unique constraint creates an index in Postgres. Okay. For the purposes of the final exam, I'm not going to ask you like what indexes have already been created, but you will need to know that information in order to answer this subsequent type of question right here, number 2. And number 2 right here is asking you to list all of the scan methods that could possibly be used for the following SQL query. And so the scan method, again, that's the way that we answer select queries, get information out of a table where we just have select from and where, and there's nothing else going on. So these scan methods are sort of like the most basic things that are always going to happen in any of our queries. And we've said that the table scan method is something that's always applicable. You don't need any special indexes for that. So if ever I ask you, like, what are the scan methods that could be used for a query, then the first thing you should always think about is that the table scan is something that can always be used. Again, the table scan being like the for loop over the heap pages. So the table scan is something that can always be used. And then the sort of subsequent question is, okay, then we have 3 index scans, and which of those 3 index scans are possibly applicable to solve a query like this? In order to know that, we have to come back and think about what indexes actually exist. And so here we're looking at the tweets table, and we have our where clause over here is on the id user column. So over here, we have 3 indexes, one on the users table, one on the tweets table, one on the tweets mentions table. And only one of those mentions the tweets table right here. Only one of those mentions the tweets table. So only one of these could possibly be speeding up our queries. The users table and the tweets mentions table can't possibly speed up this query that is on the tweets table. And up here we also have this this id tweets constraint, or we're making the index on id tweets right here. And so the where clause, in order to speed things up, in order to do the search through this B tree, we have to be searching through the id tweets column. Down here, we're not searching from tweets based on id tweets, though. We're searching based on the ID user right here, and so we don't currently have an index on the ID user, and so there is no index that can speed up this where clause right here, and so none of the index scans are applicable. The only scan that's applicable is that table scan. Front to back. Henry first.
Is a table scan the same thing as
Yeah, so the question is that in the notes I wrote it as sequential scan. Here I wrote it as table scan. Yeah, synonyms for each other. Table scan, sequential scan. Avizer, you had a question as well? So up here we have an index. We do have an index that mentions the ID users column right here, but this ID users column is inside of the users table. And so because we're searching here, not inside of the users table, but inside of the tweets table, that index can't help us out. That here we're searching on the tweets table, so it needs to match tweets right here, tweets and tweets. Does that make sense? Yeah. Ethman? Yeah, so the question is, let's review again which scan method you can use in which situation. And the answer is that, first of all, a table scan can always be used. In order to use one of the index scans, if we come over here to the the index scan section, there is a brief section down here at the bottom about the optimization of like when Postgres is likely to choose one of these scan methods over another method. But it's not specifically like listed in these notes right here, like what are the physical requirements that make it physically possible to use a scan method. So let's mention that, I guess, explicitly right now. What does it physically have to do in order to use a scan method? Well, the index right here, tweets, id tweets, this is an index on the tweets table and the id tweets column of the tweets table. So in order to use this index right here, in order to use that index, we would need a query that is referencing this column of this table. So something like select whatever from tweets. Oops. That's a typo right there where id tweets equals whatever it equals to. That if we have a condition like this, then the table that we're searching and the columns that we're using to do that filtering all match up here. And so it makes sense that we can use this, this index right here. In this case, we can do, we don't have to care about what the columns over here. We would be able to do either an index scan or a bitmap scan. Index scan or bitmap scan in order to answer this query up here. In general, anytime you can do an index scan, you can also do a bitmap scan. The bitmap scan is the most general of things. Then the index scan is sort of like a subset of bitmap scans. And the index only scan is a subset of the index scan on when you're allowed to use it. In order to use the index only scan, the column list over here also has to be all this information contained in the index somehow. So in this case, the only thing that's contained in this index up here is this ID underscore tweets. And so if the select over here was ID underscore tweets, then we could use the index only. But if this was mentioning any other columns at all that are not contained directly inside of the index itself, then we would not be able to use the index only scan and have to resort to one of these other two scan methods down here. I guess the number one thing to make sure that you understand is that on an index, the table that you're selecting from has to be present and the column that you are doing the where clause on has to be present in order to do an index, any of the index scans possible. And if those things aren't present, then there's no way you can use it. The other sort of conditions are all lots of, I don't know, subtle edge cases. Again, we've only talked about like half of them because the other half are buried in the reading. But I guess the most important of those other edge cases is that when the index only scan can be used, and that's when all of the columns referenced anywhere in the select query are contained inside of the index somehow up here. Good question. Henry.
There's kind of an alternation ID user and plural as the name of the column. Is that intentional?
Let's see. So yeah, up here I have ID users as the actual name of the column up here, and then down here, sometimes like here I have ID users plural and ID users singular over here. You should just think of that as like a typo, that should be a plural thing. So these should be ID underscore users plural. Good question. Any other questions so far? Okay, based on that previous discussion, hopefully problem 3 will be relatively straightforward, something that makes sense to us. It's, again, list all the scan methods that could possibly be used for the following SQL query. And so several differences between this query down here and this query up here. The first difference is that the table that we're doing the from over, up here we have from tweets, down here we have from users. We have a different table over here between these two queries. So we know that it'll definitely be a different set of indexes that could possibly be applicable. The columns are the same that we're doing the where clause over, and the columns that we're selecting also different. In this case, we now need to look at the users table. What indexes exist on the users table? That's this first index up here. We have a index on users, ID users. And so here the users and ID users, that does match. Users and ID users does match our index. And so I guess, again, we always know that we can do this table scan, or I'll write it out as sequential scan this time. Sequential scan, and sort of the same thing as the table scan. But now we can use the index because the table and the columns match. So if those tables and the columns match, you can definitely do an index scan, or a bitmap scan. And now the question is, can we do an index-only scan? In this case, we're not just trying to find the ID users over here, not just reporting that value, we're also reporting the username right here. We're also reporting the username. And so because we're reporting the username is not listed in this index anywhere, only the ID users is listed. The username is not listed. And therefore, in order to get that username value, we will have to reference the heap table. And so we do need to use either the index scan or the bitmap scan. We cannot use an index-only scan. So only these 3 scan methods are applicable for problem number 3, and not in particular the index-only scan. Yes? Sorry, it's okay. So the question is, why no index-only scan? And the answer is that in order to do an index-only scan, every column that is mentioned down here, must be present inside of the index in some way. And the only index we have on the users table, the only index that we currently have on the users table contains only the ID users column. And so an index-only scan implies that we're only looking at the index for the information that we're trying to get, and the index only contains the ID users column inside of it. Therefore, if we're looking for any other columns in the table, we can't possibly only look at the index, and we have to also look at the table. In this case, we are also looking at this username column right here. We are also looking at that username column. And so we can't do the index-only scan because of this username column right here. If that username column was not there, so if this was not included, that would imply that an index-only scan possible. So IDX, abbreviation for index, index-only scan possible. Similarly, if we had a different index that was created, so if we had, draw a line right here, if we had an index on now users, and instead of just one column inside of the index, we had multiple columns inside of the index, in this case, ID underscore users and the username, then that would imply also that an index-only scan possible. Index-only scan is possible. Again, because all of the information that we're trying to access inside this query is actually physically contained inside this index. And so there's no need to reference the heap table to get the username column now because the username column also included inside the index. Wow.
Sorry, are you saying so if there's for conditions with so like we have to do conditions for two different columns and those columns are inside this list?
Question is two conditions on two different columns. Here, that's a different situation than where we're at right now. Right here, we have only one condition on one column right here, ID user equals ID user. And then on the left-hand side over here, we have two different columns right here. There's no conditions on these columns. These are the columns that we're trying to return as part of our select statement. So the only column that has a condition on it in this case is the ID user, but we're trying to extract also the username as well. And if that username is included in the index, then you're able to do that. Does that answer the question?
But what about the situation where
Okay, so the question is now, what if we had multiple conditions over here and that were on multiple different columns, and we'll get to that in a later example down here. Yeah. Great questions so far. Any other questions? Yes.
So the bitmap scan requires the same thing as the index scan, where everything referenced by the layer clauses has an index.
The question is, what exactly are the requirements of the bitmap scan versus the index scan? And the answer is that anytime you can use an index scan, you're also able to use a bitmap scan. The bitmap scan is more general than the index scan. It turns out that the bitmap scan, you can use it on multiple indexes at once. The index scan or the index only scan, you can only use it on a single index at once. But we're not going to talk in class about that more general bitmap scan functionality. That's something that you'll have to do read the chapter for. But maybe let me come over here just so that I've said this out loud, but I want to make sure I write it because it's an important thing to make sure that, I guess to understand here. The order in terms of applicability is that you can always do a table scan or the sequential scan. Table scan equals sequential scan. You can always do that. Then the next most general is a bitmap scan. And then the next most general is the index scan. And the least general is the index only scan. And on any given select query, if you can do something lower down in this list, if you can use something lower down in the list, then you're guaranteed to be able to use whatever is above the list. You are guaranteed to be able to use the scans above. So you can think about this as like table scan is somehow like greater than or equal to bitmap scan, which is greater than or equal to the index scan, and greater than or equal to the index only scan. And as you're doing the reading, trying to make sure that you fully understand all the little like sub details of these things, this is a good way to check your understanding about what's going on, understanding what's the situation where one of these is applicable and the other one is not. Good questions. I'll leave this up for another second or so if people are writing things down. Any other questions at this point? Oops, that's not what I wanted. That. So number 4 down here, a new table now. So explain why the following SQL query is likely to be inefficient and create an index that will speed up the query. So this is similar in spirit to the previous problems that in order to first determine why this query is likely to be inefficient, we need to think about what are the scan methods that are applicable to this query. And then once we do that, we can think about which scan methods we would like to be applicable and create an index that will make that new scan method applicable. In this case, we're on the tweets mentions table instead of the users or the tweets table. And we're only getting this ID tweets column as a result, mentioning the ID users down here. So let's come up to our create index right here and think about what indexes, what scan methods are applicable based on this index up here. We have a create index on tweets underscore mentions, ID tweets, ID users. And again, the table scan, sequential scan, always going to be possible. So sequential scan. But now my claim is going to be, so this is the first sort of index that we're really going to be talking about with two different columns inside of it. And my claim is going to be that the way these columns are structured, we can't use any index scan. So here we have create index on tweets mentions with id tweets, comma, id users. So what we currently have is id tweets, comma, id users. We have id tweets, comma, id users. And it will turn out that because we're filtering on id users right here, change my color, still reddish, because we're filtering on id users right here, and id users is the second column over here, it's the second column, we are not going to be able to use any of the index scanning strategies. In order to understand why that is, I'm going to switch my screen over here in a second to the chapter. We'll see a picture about how these multiple column indexes are physically stored, and we'll talk about that, see why the second column information over here is not useful if we have an equality constraint like this. But I guess the most important takeaway at this point, the thing that we're building up to explaining why, or the thing that we're explaining right now, is that if you have a where condition in your select clause, then this column that's in the where condition must be the leftmost column over here inside of your index. Here we don't have the leftmost column over here inside of the index, and so we won't be able to speed up the index. We won't be able to use an index scan, and we'll explain why right now. Coming back over here, I'm going to go to our chapter notes over here. This is the last picture that we sort of talked about on the B tree index. And all the pictures that we've seen so far, again, these square boxes are the individual pages. These sort of rounded boxes inside, these are the tuples inside of the page. And all of these tuples currently have only one column inside of them because the create index command only had one column that was listed in the create index command. If we scroll down here a little bit, though, the next example that they're going to have is from a multi-column index. And there's a lot of text over here that explains exactly what they're doing. Eventually, we'll get to this picture down here that has a multi-column index created. So here, this is their create index command. You can see they're creating it on this table called aircrafts. There's this big complicated condition in the first spot, but then there's this model here in the second spot. So there's a comma right here. So there's two things that are being stored inside of this index. This is the first thing right here stored inside of the index, and this is the second thing down here stored inside of the index. This whole first thing up here will evaluate either to the number 1 or 2 or 3, and this down here will be a string, the model of a type of airplane. And so coming down here, we can see what that looks like as an example, that now each one of these square boxes inside of the index represents one page inside of the index, and each one of these little circly boxes inside of the page represents one tuple. Now the way they're representing the tuple, though, is that it has two pieces of information inside of it, not just a number, but also this text. Again, these two pieces of information come from the create index command up here, where this thing up here is the first piece of information and this thing right here is the second piece of information. And in this case, they have a big, long command that evaluates either to the number 1 or the number 2 or the number 3, and then the model of the airplane. And so we have either the number 1 or 2 or 3 on each of these at the top being the first location in the index. And then the bottom is the text, which represents the model of the airplane. When you have two columns inside of an index, the important thing to understand is that everything works exactly the same on the first column. So here, when we have, let's say we're searching for the number 2 inside of this index, then we know that the number 2 is going to be contained between this location right here and this location over here, for example. And we can't have any 2s inside of this location over here because the 1 right here takes us to the very leftmost value over here. And so we come down, follow here, we get the 2 value right here. And these, if we look at the leaves down here, on the top row, row of the numbers, everything is sorted according to the number. Everything is sorted according to the number. Or in other words, everything is sorted according to whatever the first column is in our index. The only purpose of these secondary columns, or how they're stored in the index, what they do is they break the tie of the first column. So here we have 3 values that are 1, 3 values that are 1. And so what order are those 3 tuples going to be stored in? Well, they will be stored in alphabetical order on the second column. So here we have Bombardier, Cessna, Sukhoi, Superjets. And because the very first column, they're all 1, we break the tie of those 1 using the next column down here. So 1, 1, 1, and then the next column down here. Similarly over here with these 2s, the 2s extending over into 2 pages like this. And again, in order to break the tie of how these 2s should be sorted, we have alphabetical on the second column, so Airbus and then Boeing. But notice in particular that Airbus is alphabetically after the Sukhoi Superjet, but because the model of the airplane is the second column, and we don't care that Airbus is after the Sukhoi Superjet. That's totally an okay thing to have happen because we have the number 2 up here in the first column, and the 2 is greater than the 1. So the 2 sort of takes precedence. Whatever's in the first column takes precedence, and whatever's in the second column only is for breaking ties. Similarly, over here, we have the 3, only one craft in this 3 category, the Boeing 777. And this is alphabetically after the Cessna and the Sukhoi, but because it has the 3 up here, that takes precedence. Okay, that was a long explanation of this picture right here, but the key takeaway here is that if you're trying to do a search, say for a Boeing aircraft, you cannot use this index for searching efficiently for the Boeing index, for the Boeing aircraft, because the Boeing could be stored at any location depending on what the very first column is. So you can only efficiently search based on the first column, and then subsequent columns not useful for doing that efficient search. If we wanted to be able to search on the second column instead of the first column, then we would have to reorder how our information is stored in the index. And if we scroll down a little bit, they have a new index created right here where the columns are in reverse order. First the model, first the text, and then the number right here. And when you do that, now everything is stored alphabetically according to the name of the aircraft. And so now we could, for example, get all of the Boeing aircraft efficiently because it's stored alphabetically according to the name. But we could not, for example, use this index to get these number categories efficiently because they could be anywhere depending on whatever the name of the corresponding aircraft is. So the takeaway here is that if you have a create index with multiple columns, it's still going to store the same information no matter which column which order you put them in, but how it searches will be different, and which queries it makes for efficient searches for will also be different. And so whatever column you expect to do your query on, that needs to come first, and the other columns, you can think about them as just like extra information being stored inside the index. I talked a lot there. Any questions about those pictures? What's going on? Yes, Emma. So there's a great question. The question is, what if I want to be able to do queries both ways? In this example right here, searching both on the name of the aircraft and searching on this type number of the aircraft. Is it possible to include both indexes inside of our database? And the answer is yes. If you know that you're going to need to be doing queries on both of those, then you'll need to have both indexes inside of your database. The disadvantage of that is then you'll have more indexes that on the insert operations or updates, deletes, you'll have to maintain those indexes, and those will be a little bit slower because of all of those extra operations. Again, more likely to have these hot tuple conflicts that will be expanding the size of your database significantly. But if you really need to do the select queries in both ways, then you need both of those indexes. And it's perfectly okay to have both of those indexes. So that brings us back to where we started with this problem, that we have this explain why the following SQL query is likely to be inefficient and create an index that will speed up the query. So on the final exam, if I ask you something like this, you'd have to be able to explain the order of the columns, why that matters, going back to the structure of the B tree, drawing a picture of the B tree for me, for example, and explaining why the order matters based on that structure. And then saying that, okay, because of the particular way we ordered things up here, because we happen to have ID tweets and then ID users, we can't efficiently do this query. But if I were to add a new query, if I were to add a new index, on tweets underscore mentions, and now change the order. Instead of id tweets first, followed by id users, first do id users followed by id tweets. That would imply that all of the table scanning strategies are possible, the sequential scan and all three of those index scans. I'll just write here that the index only scan is possible. Again, that's the fastest of the scanning strategies, so that's the one that we're most interested in being able to do. And if we're able to do that scan strategy, we talked about that implies that since it's at the bottom of this hierarchy over here, that you can do any of the other ones as well. So very sort of semantically, there is no difference on this unique constraint, whether the unique constraint is on id tweets, comma id users, or id users, comma id tweets. A primary key on both of these two things is 100% equivalent semantically in terms of what constraint it's enforcing. But performance-wise, you'll have different select queries that you're able to do different queries with more efficiently. So the order here can matter for performance-wise, but it's not going to matter semantically about what constraint the table's enforcing. Front to back first, Henry.
So could we also add just a new index on tweet mentions ID users and not have ID tweets as the second part of that index? Because that would also speed up this particular.
Yeah, so the question is, what if instead of adding the ID tweets over here, could we just have create an index on ID users? And the answer is that would speed up this query. That would make an index scan possible and a bitmap scan possible. And if you were to tell me that on the final exam, I would say that, yes, that's great. And then I would ask, how could I make an index only scan possible? In which case you would have to provide this this further index right here that has both of them inside of it. Or if you just jump straight to this, then I might ask, like, okay, what would happen if we took out the id tweets column right here and only had the id users column? Would that still speed up this query, or are there still are we stuck only with the sequential scan?
Why is an index only scan possible if you have ID tweets but not just have ID?
So the question is, why is an index-only scan possible if we only have ID users but not ID tweets? The answer is because up here we have the ID tweets as something that we're trying to return. We're trying to return all the tweets that correspond to a particular user inside of this table. And in order to do an index-only scan, all the information must be contained just in the index, so we don't have to touch the heap table at all. If we don't have this ID tweets right here, only have ID users, then in order to actually get the ID tweets value, we have to look inside the heap in order to extract this particular column. So that's why in order to do the fastest possible scan, the index-only scan, you need both of these columns right here. Yep. Yeah. Okay.
So if we still had the other create index that we made before with IDs first, would we be able to do an index-only scan since we have separate indices on both?
Good question. The only so index-only scan and index scan only they require they be on the same index. The only scan method that's able to use multiple indexes at once is the bitmap scan. So the table scan uses 0 indexes. The bitmap scan uses 1 or more indexes. Index scan and index-only scan can only use exactly 1 index. And again, how the bitmap scan uses multiple indexes, not something we'll explicitly talk about in class here. Good question. Does that answer the question? Yes.
So in the final exam, when we're explaining to that we're going to like create an index to make an index only scan possible, is it enough to just say like we need to create an index on this table mentioning these columns, or would you want to send a specific thing like we can certain things that this table?
So the good questions about like what exactly, where's the dividing line on things that you have to know for the final exam, or ways that you might be able to lose points on the final exam if you don't know something. The answer is that you guaranteed you can't lose points on the final exam for not knowing the syntax of something. So if you forget the syntax of like, I forget how to create a primary key, or I forget what is the exact syntax for creating an index, guaranteed not to lose points for that. As long as you're able to explain that, so like here, for example, I didn't actually write out a full create index command. I just said that, okay, the index has to be on tweets mentions, and it has to mention these 2 particular columns in this order. So syntax things, not important. Any sort of semantic meaning thing, though, will be important. Basically, in order to get a perfect score on the exam, you'll need to be able to talk about all the semantic meaning things about all of the things in the reading chapters. In terms of, so grading wise, the exam is going to be next week as we get closer. I'll talk a little bit more detail about this. But so it's 20-ish% of the grade. I think it's 64 points is what I said. Whatever works out to be about 20-ish% of the grade. That first like 10 to 15-ish% of the grade, I will be trying to find excuses to give you points on things, finding things that you know, and so that I can give you those points. The very last like points in order to get from like that C-ish level to the A-ish level, that's the point where I'll be starting to ask like hard edge case questions about seeing how deep the understanding goes. So hopefully that sort of answers the question. Nico. Question is there an answer key for the practice problems? I don't think so. I have one more set of these though that I'll give you, which is printed versions of previous final exams, and those do have answer keys. So I guess this final review 1 and this final review 2 over here, no answer keys for those. I have some more that I'll give you next week that do have answer keys. So you can test these do what you think, and then show me in office hours or after class or something, and I can say yes, or you missed these things. Okay, I want us to make sure that we cover the join strategies today. So problems 5 and 6 and 7 and 8 here, all covering those same things that we've been talking about before, just in more edge cases things, in some cases talking about things, again, that we haven't covered in class yet, but are part of the reading. And so you need to understand the reading in order to get them fully understood. But we're going to jump down here to problem number 9 and talk about these join strategies right here. Down here, problem number 9, the difference between 9 and the previous problems is that in 9 we have this join keyword right here, and so we have 2 different tables that we are working with. It is in Postgres and in every database that currently exists, you cannot make an index on multiple tables. Cannot make an index on multiple tables. And that's a fundamental concept or a fundamental property of Postgres. They definitely want to just like beat that into your head before the final exam, and never suggest to me that you're going to create an index on one index on the tweets mentions and the tweets table at once. So how do we speed up? Queries that use multiple tables? And the answer is we'll have to create appropriate indexes on the tweets mentions table and an appropriate separate index on the tweets table. And there are 3 join strategies that have different properties, and we'll go over what those 3 join strategies are next and how to apply them to a problem like this. So coming back over to our class notes right here, scrolling down /join, oh man, GitHub breaks the slash keyword. Join strategies right here. Last thing in this topic 10 indexes B tree section that we'll be talking about, the join strategies. And these are used, again, anytime there's any type of join, whether it's across, an inner, or left, right, full, outer join, doesn't matter what type of join is going on. These join strategies are the techniques, the algorithms that implement those joins. Again, there's 3 of them. And Postgres will automatically determine which one of these algorithms to use depending on which will be most efficient for your particular problem. So the simplest one, the nested loop join, this is one that can always be used. And this is similar to how the sequential scan is like the backup fail-safe option. This is the backup fail-safe option for the join strategies. So it works in all scenarios, including without an index. Here's what the pseudocode looks like. So again, there is a link up here that you can reference, read through what these join strategies look like. But all of the really important things are included down here in the notes for the join strategies. And the pseudocode is the thing that if you understand the pseudocode for each of these join strategies, then all of the things like the runtimes of the join strategies, when you would use one versus the other, sort of become obvious. So my recommendation on how to study these join strategies is to first just understand the pseudocode, and then from there, make sure that things like the runtime become obvious. So what does this pseudocode look like? It's called a nested loop join because there are 2 for loops, one nested inside of the other. And we just loop through every row in A, then for every row in A, loop through every row in B. If we satisfy whatever the join condition is, then we'll output that combined A comma B row. Here I'm using M as the number of rows in A, in as the number of rows in B. And so the total overall runtime for this algorithm is going to be 2 nested for loops multiplied together. You get the O of M times N runtime. These tables, as either of these tables grow large, that's a quadratic runtime, so very slow, and so we can solve this way, but probably not the most efficient way to solve this. Well, let's see. Little historical aside, back in like the early 2010s, mentioned that like these NoSQL databases getting super popular. One of the reasons NoSQL databases got really popular is because they don't allow joins. And so because you don't allow joins, you never get a potentially quadratic algorithm appearing. And so a lot of people who didn't understand how to make joins fast liked having that restriction where they would never accidentally get this quadratic runtime. SQL databases like Postgres have a reputation, undeserved, of being slow by people who don't understand how to make joins fast, and so they're always stuck with this quadratic runtime. But we're going to understand how to make these joins fast, much faster than quadratic, and so you won't be stuck with this performance problem, and you'll get very fast runtimes. So that's our pseudocode here, again, quadratic. If you do have an index, though, the nested loop join can speed things up a little bit. So nested loop join with an index on B, the index on B being the inner query right here, the inner condition right here. Then we can replace that inner for loop with an index scan, whether it's an index-only scan, an index scan, or a bitmap scan. In some sense, it doesn't really matter, but we can replace it with any one of those scans, and now we'll have a linear time runtime on this outer for loop and some sort of logarithmic runtime on this inner loop. The constant factor, again, of this runtime will depend on exactly what type of scan there was on the inner side of this loop, but much, much faster logarithmic runtime instead of linear runtime. And so we go from quadratic down to this imlog_in runtime. Furthermore, if there is a limit k clause, then we don't have to do this entire outer row repeatedly, the entire length of the table. We can do it only k times, and so the runtime can be reduced even further down to the theta k log in right here. Again, I'm being very careful with all of these thetas versus O's versus omegas. I don't believe there are any mistakes in here. So you should make sure that as you're working through this, understanding what's going on, understanding why I chose a theta in one location instead of another location, or instead of an O or instead of an omega. Okay, if you have the index on B, then you do the index search on that inner loop. If the index is on A instead of B, though, then recall that joins are commutative, so you can switch the order of the join, and then, so in this case, do the for loop on the outer B, the outer for loop on B, and the logarithmic search inside of here, and get k log m or n log m down here instead of m log n. So the m and the n, you can, Postgres will choose whichever one of these two numbers is larger between the m and the n, and move that into the inner of the for loops so that it does the index search on those. So that's the nested loop join, the simplest of the join algorithms. The hash join, a little bit more complicated, has a little bit more requirements here, and the particular requirement is that you have an equality join condition. So the nested loop join, again, always works. Normally we have equality join conditions, but if we have weird join conditions that are like less thans or greater thans or something that's not equality, you can always use the nested loop join. For the hash join, you have to have an actually equality in your condition. Some sort of technical parameters too, or conditions about the size of your hash table fitting inside of your working memory. And a note here that hash joins have a large initial overhead to build a hash table. But the pseudocode, what it looks like is that for whatever our outer, we pick one of the tables and we create a hash table on that table. In this case, I've written it so that we pick B as our hash table. B will have size of n. And then for each row in A, so the for loop here taking time m, we'll do a hash table lookup right here. Do a hash table lookup, and the hash table lookup, at least in theory, is constant time. And so all of this happens down in constant time. And so we've reduced the runtime to m plus n instead of m times n. The disadvantage of the hash join, again, though, so this is a very good runtime, m plus n, very good runtime, linear in both of the sizes of our tables. Disadvantage, you have to have this equality join condition, and there's this large overhead before you can start outputting tuples, because you have to do this entire hash table right here. as an example of where that large overhead is important, if you have a limit k clause, you still have to build the entire hash table up here, and so you can't quite take as good advantage of those limit k clauses. Postgres, if there are no indexes, probably will prefer a hash join over a nested loop join for very large tables. But otherwise, if the tables are not extremely large, it's going to prefer the nested loop join. Or if there's any indexes created, it's going to prefer the nested loop join. The last of our strategies here, the merge join, is the fastest, best condition, and this is the one that we'll try to develop indexes so that it will always do a merge join. And the idea is that this is like the merge step in merge sort. It requires that all of our inputs be sorted from both of the table scans that we're joining together and an equality condition that we're joining together. And so if the data is already sorted, there's no overhead, and we can do an early stop, taking full advantage of the limit clause. So very fast if the data comes in already sorted. Again, it's like the merge step in merge sort. So this is just pseudocode for that. The runtime, again, is the im plus in, so the linear in both of these operations, and there's basically no overhead. So it's very fast, best case scenario for all of our joins, and what we should always try to achieve. We just have a couple minutes left, so I'm going to jump over here, and we'll see how can we make a merge join happen in this for this query right here. In order to make a merge join happen, first of all, can a merge join happen? We have the constraint that we can only do it for an equality join condition. Anytime you're using the using clause right here, that implies an equality. So the using is equivalent again to the on tweet underscore mentions dot ID tweets equals the tweets dot ID tweets. So anytime you have this using clause, then you are using an equality. Similarly, anytime you have a natural join, you are using an equality. So we've satisfied that condition. All we need to do is somehow be able to scan the tweets mentions or the tweets and the tweets table on this column over here so that we're doing an index only scan from both of those so that we get the things back in sorted order. Or sorry, an index only scan or an index scan would work. In this case, what we need is we need some sort of index on tweets mentions of ID tweets as the first column. Could have more things inside of it, but that at least as the first column so that we get things in order based on ID tweets. And another separate index on the tweets table, also on ID tweets. In this case, we already have an index on the tweets table, ID tweets, that was created by the primary key up here. Again, the primary key on the tweets table is on ID tweets, so we have an index right here. The tweets mentions table up here, the primary key has ID tweets as the very first thing, and so we can also use that. And coming back to problem 9 here. So it turns out that we don't need to create any new tables, we don't need to create any new indexes. We already have the appropriate indexes that allow us to do the merge join right here. And so no new indexes needed to do a merge join. No new index needed for the merge join. Some of the, there's some more complicated examples going on next. We'll go over those next time in class. We'll also start going over more different types of indexes next time in class. The lab again tomorrow, reviewing how putting it into practice, making actual SQL queries fast, and your homework that's due 10-ish days from now, also making SQL queries fast, putting all this stuff into practice. If anybody has questions about anything, I'll stick around after class. I have the office hours today as well to get questions answered. Otherwise, I will see you all later. See you all tomorrow.